Es un material de la comunicación por correo ni nada. Usually works
Maybe I need 10 seconds to know what's happening. You will go. I mean, you will not complain about it. So I guess so the microphone is over there, just to know.
Yes, the microphone is here, okay. But I think there is no problem. They are going to hear you well. So, good afternoon. Welcome everybody, people in the room, and also the people that are connected through Teams.
Now 10 people.
Great. So today we are lucky that we have Dr. Johann Fellner with us. He's going to tell us about recent research in waste management or in waste and resource management. He comes from the Vienna University of Technology, from the Institute of Water Quality and Resource Management. He has a very strong group in waste and resource management. We have met him some years ago. We have sent some doctoral students to his group, and he has been really, really nice with them. They have learned a lot. And Juan, who is there, is really happy that he went there some years ago. And well, we have asked him to present the things they are doing. Okay, so this is what he is going to tell us today. Thank you, Johann.
Thank you very much for the invitation. I'm very glad to be here. I think that's the first presentation I'm giving with 2 years of delay, or more than two years of delay, because the idea was already to come over here in March 2020, but you know what happened at this time. But I'm glad to be here now. Yeah. Topic is recent research in waste and resource management at our institute, what we are doing, and I mean, I'm trying to give you 4 examples. Maybe I will be only able to show 3 examples of what we have, 3 research projects. Let's see how fast I will be. At the very beginning, I would like to spend a few words about the university I'm coming from. That's the Vienna University of Technology, more than 200 years old. So we celebrated 7 years ago our 200th anniversary. We have about 30,000 students, and it's located almost in the center of the city. Yeah. When it was founded, 1815, it was outside the city gate. Yeah. We have a lot of partner universities. I mean, I guess this picture is not very actual. In the meantime, so probably there are much more. But yeah. How many people are working there? About 5,000 staff members. And from these 5,000 staff members, about two-thirds are paid by the government, are paid by the university, and 1/3 is financed by research funds. And the overall budget is about 300 million euros. And again, 1/3 is coming from research funds. So that's the budget, the annual budget. Yeah, I said already, 30,000 students. We have about 20% foreign students, and altogether need to check also 7 faculties, some architecture, civil engineering. In the meantime, it's called civil engineering and environmental engineering, informatics, electrical engineering, yes, thanks. Mathematics and geoinformation, mechanical, industrial engineering, physics, and technical chemistry. And you see the different faculties have different numbers of institutes. So our faculty has an average number of about 8 institutes. Some others have 14 institutes. And most probably they are also forced to reduce the number of institutes. Because simply the idea is to have less, less administration, and they think this would help. But yeah, that's another topic I could talk another 2 hours. I don't know. That's our institute. We're altogether about 60 or 70 persons. It's the Institute for Water Quality and Resource Management. And this institute is divided into 2 more or less research centers, or research groups. One is on water quality management, so everything which is related to water quality, starting from water supply, also to wastewater treatment. So these are the wastewater treatment guys. They are also very much focusing on nutrients, nutrients introduction into the groundwater and into the water basins. So that's their specialty, and we are looking to all the stuff which is solid waste and resources. So here you see water quality, water supply, nutrients management. And yeah, this is our topics, typical processes in landfills, incineration, recycling, resource management, how to have an overall management of the resources, not just only focusing on one particular process or one particular issue in waste management. This is now the Research Center for Waste and Resource Management, so this is part of the institute. We are about 22 persons, and yeah, these are the research focuses, which is at the first glance very much on this called material flows, material flow analysis. I will show 2 examples what we mean by this. It's a very simple tool, but very effective tool we are using. Then another important topic we are dealing with is urban mining and circular economy. I will have a talk tomorrow about this. And then we also focus very much on the characterization of waste, on different type of waste, because only when you know the composition of the waste, you know also what is the best solution for the waste. But it's not only about characterization of waste, it's also characterization of waste management processes. So knowing what is happening if we send certain type of waste into a sorting facility, how much of the waste is really sorted to the target fraction, how much of pollutants are in the target fraction, and so on. So we are also doing the characterization of waste management processes. And the final topic, and that's also how I start to enter the group, is landfills and final sinks. So the places where we finally dispose of our waste, which we cannot recycle or reuse or recover. And that's where I also did my PhD a long time ago. The group maybe. These people, all of them are paid by the university or by the government, and the others are project paid stuff. Some of them are just 20 hours per week, so not all of them are full time at the moment. Or that's also outdated already 2021. We had 18 projects, 18 research projects, or 18 projects running. The majority was research project, and we had also some kind of training, so educational projects, where we, at this time, we had a project with, what was that? Educational project in Indonesia, and also in Serbia during this time, and then a networking project, which is was a European cost action, where to link different institutions together. And the funding of these projects was 70% national and 30% international. So yeah, another statistics that we can. What we also did during the last years, we developed a lot of different, and that's where we are would like to focus also more in future. We try to develop different tools, different software tools. The most famous one and the most used one is the first one, and it's the oldest one also, is the software for materials and substance flow analysis. I think it has globally maybe 10,000 users or something, so a big number already. And you can download the software, or most of the softwares are available for free. Yeah. So the second tool which we developed is a software for waste incineration plants to determine their biomass content or their CO2 emissions, and I will talk about that during my presentation today. Then we have software recently developed, which is not publicly available, about for landfill operators to evaluate which strategy for landfill aftercare is best and how they can manage the aftercare, because a landfill, after it's closed, needs a long time aftercare. And with this tool, the operator can, on the one hand, estimate how many years and which options you should follow. Either you should put a very dense cover layer or try to get a lot of rainwater in there so you can play around. The next tool was developed for the Belgium waste, or the Flemish waste authority, OVAM. They were very much interested in landfill mining projects, meaning digging out landfills and trying to recover, on the one hand, material resources, but on the other hand, and this was much more important, or is much more important in Belgium, to recover the land also, because the land is a scarce resource there, because it's heavily populated, and they have a lot of old sites, and the pressure on the land is increasing, so they would like to reuse the land, and basically you can do that by these landfill mining projects, and they would like to have a very simple tool to evaluate, based on a few indicators, whether this project pays off from an economic point of view, because the land price is so high, or the resources in there we can recover generate so much value that the costs are covered.
Excuse me.
Yeah.
The biomass software.
The biomass software?
Software, yeah.
It's free.
This one, yeah, you can download. You can download a trial version for free. But the full version, is not for free. Yeah?
Okay.
But for universities can, it's dedicated for operators, but universities can get it for free.
Okay.
And the last one, and hopefully I will talk about that on Friday, was developed during a project with the United Nations Industrial Development Organization, UNIDO. It's a waste management planning tool for emerging and developing economies. So municipalities there also face troubles to know which waste solutions they should follow, what about the costs, what about the climate impact, and so on. So this is also a recent tool, and I will talk on Friday hopefully about it. This one again can be downloaded for free. So a main goal of all our research activities is to understand the material turnover we are generating. So you can imagine when you investigate your personal material turnover, you need to know how much food are you taking in, how much excrement you are producing. Okay, that's your personal material turnover. But a city or a country or a region has also material turnover. We need construction materials, we need fossil fuels, we need water. And this is a picture of the city of Vienna. It's already a bit old, a bit outdated, where, long time before I start to work there, they try to investigate what is the material turnover of the city, okay? How much water is going into the city, and the data are given in tons per capita and year. And at this time it was about, 12 to 18 tons of construction materials and consumer goods are going in there. Of course, the biggest part is the water, water consumption. But what I would like to make stress on, and what is very important also when we talk tomorrow about circular economy, we use certain materials, and on the other hand, we generate waste. So waste is all the time a mirror of what we consume, okay? But, and this is very important, that applies to, I would say, almost all societies today still, is that a lot of the materials we consume, they still accumulate. You know, our cities are still growing. Our goods, what we own, are still on the growth. Yeah. This means for a circular economy that the output here, the waste, even if we recycle at 100%, will never be able to cover our demand. Okay. Because there is a lot of materials still, I would say, stored here or stocked over a longer time. Yeah. And as long as that means we are still on a growth, the material growth rate. Yeah? And as long as we are in a material growth, we never can close our circles totally. Okay, so I would say when we talk about something like a unique selling point in research of the institute is this methodology of material flow analysis. Yeah? Where we developed also the software, and where the previous professor, who's retired already since a few years, was a pioneer in developing this analysis and trying to apply it in waste and resource management. And the first two examples I would like to show is how we are trying today to apply this and what we can learn out of it. Okay? So it's about plastic management in Austria, so where we apply this methodology of material flows. And it's rather simple. We just balance what goes in and try to trace the flows through the whole economy, starting from the production to the waste management. And the second one is about steel flows and steel recycling, steel circles in the European Union. A PhD which was recently finished. Then I would like to talk about the software, about the methodology, how we determine cost and CO2 emissions from waste incineration plants. And yesterday we had a very interesting conversation about this. And finally, and let's see how long my voice is working and how long you are still awake. Maybe I will also talk about mental research. Okay, so let's start with the plastics. Plastics management in Austria. Plastics is, I would say, the hottest topic, or one of the hottest topics now in the environmental field, together with climate change. So that's the reason also that we were working on plastics, and plastics are used in so many different applications. And very often I have students, bachelor students, and when I talk with them about plastics, they say, "No, I'm not using plastics." Like they go to the supermarket and they don't know, buy to special markets where they don't buy plastic packaging, yeah? And then usually I'm asking, and how are you recharging your mobile phone if you don't use plastics? Yeah? So then they start to think, okay, plastics is almost everywhere. Yeah? So we have a lot of different applications, and also a lot of problems. I mean, plastics are very beneficiary because they are very light, they can be structured in different ways, they have different properties. But we also face some environmental problems. Just a few figures. That's the global production of plastics. In 2017, it was 350 million tons per year, the global production. And today, 2021 or 2022, it's already 400 million tons. It's an incredible increase, and it's projected that till 2035, it's 700 million tons of plastics. So it will double within the next 17, 18 years. At the European level, plastics production is not on that high increase, so we are more or less, I mean, there was an increase in these 2 years, but in general, the production is more or less constant already, but that doesn't mean that the consumption is constant. The consumption is still an increase. We are just importing more and more plastic products. Okay. And one aim was to evaluate, or the project, what we did there was to evaluate for the environmental ministry, what about the plastics management in Austria, how much plastics are out there, how they are currently managed, how they will probably be in future, I mean, what will be the generation in the future. And therefore, we applied this so-called material flow analysis, okay? And as I said, it's very simple. We divide our economy in different processes, starting from the plastics production, manufacturing of plastics, then the plastics are going to the consumers, so we consume it, and part of the plastics are, I don't know, used as a window frame or a flooring, so they are in, we call it stock, they are stocked, yeah. And finally, the plastics which are wasted are going to waste management, and then either landfill or incinerated or whatever, and then part of it which is recycled is going back into that. Thank you. You know that I need a lot of space. Okay, so this is a very simplified, yeah. In reality, what we finally analyzed, and now you'll be a bit scared, it looks more complicated, yeah. Okay, so we again have here the chemical industry, which produces the plastics, and we consider also the trade of the plastics, because we have a lot of import and export of different plastics. Then we have the Austrian manufacturers. And then everything which is yellow are the different, how to say, consumers of plastics. Okay, so we have a lot of different consumers. Packaging is one consumer. The building and construction sector, I think it's harder to read. Building and construction sector, the transport sector, so also in the car sector we have a lot of plastics. Electronics, furniture, agriculture, medicine, household equipment, textiles, and so on. So all of them, they use plastics. And all these numbers have been determined by different statistical data in a different manner. You know, I mean, for some of the data, you just can go into the statistics and see, okay, this is the amount of plastics which have been imported. Yeah. For other, there are not so detailed statistics for packaging. Also, there are good statistics out there. But for example, how much plastics are in the cars? There is no statistics. But simply you are using at that point, you are trying to know how many cars are sold in Austria. So there are statistics out there. And then you know the average content of plastics in a car. So by combining these numbers, you can also finally generate how much plastics is in the transport sector. Okay. I don't want to go into the detail, but just to explain you, okay? And then out of these consumption sectors, wastes are generated. They're also determined by different statistics or in different ways, like how many cars are deregistrated, or how much e-waste is generated, and so on. And then it's going into the waste sector, waste collection and sorting, and from the waste sector, it's then going into the different treatments, okay? Either it's recycled, meaning that it's returned back into the production, or it's reused, which is very less. All the numbers, sorry, here I didn't talk about. All the numbers here are in 1,000 tons a year. Meaning, I think I have later on some summary. Part of the plastic waste is also chemically recycled in Austria. Then the big part is going to waste incineration plants. And then another major part is going to cement kilns. So they use it instead of coal. And finally, a very, very tiny part is going to landfills, okay? Because we have basically a ban for plastics to be landfilled. So this is now a summary, or it's easier to read here probably. So let's start here somewhere. Okay, the production in Austria is about 1.1 million tons of plastics. And then we have some net import and then some export. And the final consumption is about 1.1 or 1.2 and another 0.1. So about 1.3 million tons of plastics are consumed annually in Austria. And this consumption is divided to the different sectors, as you see here. So you can see which sectors are quite important. This is, of course, packaging, but also the construction sector. We see also how much production waste is generated, which is about 130,000 tons. And then from the different sectors, different quantities of waste are generated. And what becomes very obvious, the packaging sector, everything which is packaging is more or less generated as a waste, yeah, at the end of the year. Yeah. Whereas when we talk about the construction sector, it shows us that at the moment a lot of much more plastics are entering the construction sector than what we are removing. Because in the past we didn't have so much plastics in our building, but today, yeah, a lot of insulation are made out of plastics, meaning that we have a strong increase of plastics use in the construction sector, and in the future, the construction sector will be definitely much more important when it comes to waste generation. Yeah, but maybe in 20 years, maybe in 30 years. Yeah. And then Austria imports also some plastic waste. And this is finally a summary about where these overall quantities of waste are then generally ending up. Yeah. And the tiny part is also emitted to rivers. Yeah. There was an investigation of the Austrian EPA to check at the river Danube how much plastics are in there. Okay. So consumption about 1.3 million tons, and then the outcome is about 850,000 kilotons. Yeah, and we see out of this where are the most important sectors and where we should probably have a very strict regulation, and probably also where we know in future that these sectors get more and more important. What about the circularity of plastics? So we try to put this figure in a circle now, okay? So we have here the primary production, or the total consumption of plastics. And out of the 100% of consumption, in the moment, about 1/3 of 34% is just stored over longer time, yeah, because we use it as a flooring or as a window frame or whatever, yeah. So this is not taking part of the circle for the moment, no, but maybe later, yeah. Then part of the plastics are in used goods which are exported. So, for example, maybe in Spain it's similar. A lot of the cars which are deregistered in Austria are not dismantled and recycled in Austria. They're just shipped to Africa or to some Eastern European countries. Yeah. Or also some electronic devices are included here. Yeah. Okay. Then there is something called non-plastics dissipation. What does it mean? Plastics are not only used, or polymers, let's put it that way, polymers are not only used for plastics, but also for other purposes. And for example, one important application of polymers is colors. So, and this is not, how to say, this is not recyclable, you know. If you have polymers and colors, I mean, they are just a dissipative use. Yeah. Then we have some waste import from outside, and this is what's coming finally to waste management. And when it's written oxidation, that means we are just doing energy recovery because we burn the plastics, okay? So that's the big part, 45%, about less than 1% is landfill, and 13% is really put back into the circle, 13%. So we could say we have a circularity rate of plastics of about 13%, yeah, which is quite low.
Could you get this data? I mean,
Yeah.
is it really recycled or?
No. This you mean the 13%? No, this is really recycled because this is what we have to say. We got data from the Austrian plastics recyclers.
Mm-hmm.
So it's not the plastics which is somewhere shipped to China and maybe they're recycled. So it's just basically about the plastics which finally end up at Austrian recyclers.
Mm-hmm.
And they need to report how much they finally generate. Yeah. So, yeah. There are different, I don't want to go here, but there are very different data sources to come to this. I mean, the picture at the end looks rather simple, but the tricky part is to come to the data and put that together. Yeah? And very often, the data don't match together, so we need to find out the reason and need to check which data source is more reliable than the other one. Yeah. Here we try to capture what's happening to the plastics in the different sectors. I told you packaging, we have the sector of use plastics in the packaging sector, in the building and construction sector, in the transport sector, and so on. And on the x-axis, you see the consumption number, the consumption. So for packaging, we consume about almost 300,000 tons a year of plastics, okay? And on the y-axis, you see what's happening to this type of plastics, okay? It's maybe difficult to read. For the packaging, I mean, almost 100% is appearing as a waste. So everything which is below the red line is waste, okay? Everything which is above the red line, which is gray, means it's just an increase in the stock. So it's not waste, but it's just an add to the stock. Yeah. And the remaining part is just the remaining part is thermally recovered. The remaining part is incinerated. Yeah. For the plastics waste from the building sector, a tiny part is recycled. It's mainly PVC recycling, and the other part is also thermally utilized. When we go to the transport sector, we have a very huge blue bar, okay, which means reuse. And in that case, reuse is, I told you, in Austria, a lot of the old cars are just exported. So we accounted these cars, which are not recycled or dismantled, as a reuse, because they are definitely used somewhere in another country. Okay? That's the reason that the plastics inside the cars are also reused. Yeah? Mm-hmm. Let's put it that way. Yeah.
Some of them come to Spain. I mean, there are people just going to Austria or Germany to buy these used
cars. Okay, but okay. Yeah. So now another summary where I just try to put together what are the quantities of waste. So the biggest sector, the biggest contributor today for the plastic waste is the packaging sector. Yeah, it's 280,000 tons, and then you see the other sectors. Okay, and the total waste generation is almost 800,000 tons. And when we look how it is managed, I said before already, the biggest part is going to waste incineration, and then cement industry. And then we have the steel industry. The Austrian steel industry uses plastics instead of cokes to a certain extent. So you need for the steel making, you need how you call it? You need a reducing agent. Mm-hmm. You need a carbon source or hydrogen source to take the oxygen from the iron ore, and the steel industry is partly using plastics. Yeah. Yeah, and then about 1/4 or less than 1/4 is recycled, and then very tiny part is reused. To say we can skip this. Then we did a similar study on the packaging sector, just on the plastics packaging, because it's the most important sector. And now we did not look to the, how to say it, before we looked to the different sectors, but here we look to different products of packaging. PET bottles, hollow bodies, like hollow bodies means like if you have a shampoo bottle, yeah? Or if you have large bodies, hollow bodies large, meaning they have how to say, a volume of more than, I think, 3 liters or something. Yeah. So you can have also, that's basically very often used in industry or something as a I don't know, not container, but in German would say canister for something to fill in some liquids or something. And then we have the films, small films and large films, so plastic films. And then some other products. And then we try to trace how they are collected, how much is sorted, and how much is finally recycled, and also how much is at the end of the day going to cement industry, which is industrial incineration, and how much is going to the waste to energy plants. This was a quite important study for the ministry because the recycling target for plastic packaging is increased by the European Union. So every country in the European Union has to fulfill higher recycling targets. And today, Austria, or that was data from, I think that was 2013 or 2015, Austria recycled 80,000 tons from the plastic sector, which is really going into new recycling products. And the input, the overall input is about 300,000 tons. So the recycling rate is less than 30% or about 30%. And until 2025, I think, the rate is supposed to go up to 50%. So a huge increase. And they would like to know which of the different products needs to be managed much better. Yeah? And we could do that. So, okay, recycling rate 26%, recycling rate, and some countries calculate the recycling rate, not what comes out from the recycling, but what goes in. There's also a strong debate about this. Yeah. Yeah. And here we tried to, and that's already, I think, the last slide for the plastics part. Here we tried to trace how are the different products, plastic packaging products managed. Yeah? And just to explain you, the upper line here, so when we talk about PET bottles, the upper line means this is the collection rate. So people in Austria, 65% of the plastic bottles, PET bottles, are separately collected in separate collection schemes. Okay, 35% is just with the mixed municipal solid waste, so it's not further recycled. Okay. And then this separately collected plastic stream is going to sorting facilities, okay? And in the sorting facilities, we lose about 9%. So this is going into the sorting facility, this goes outside the sorting facility. So we have just 54% of the plastic bottles left. And then we go to the recycling process, and then again we have losses. So after the recycling process, finally we have just 45% of the material. And what we see here, example films are collected to a large extent, at least that's what the statistics is telling us, but we lose a huge part of the films in the sorting process. Yeah? So we could improve the sorting process to get much more of the recycled material here. Yeah? So the diagram shows you, I mean, because also this gives you the relevance, the overall relevance. Films are very small, very important because they count for a huge quantity, which products we should better focus on. Yeah? Okay, and here is the recycling target till 50% until 2025. Okay, so that was about plastics. Are there any questions? Yep. Yes.
So what about the MVP plans? Don't you recover some plastic from there?
We have, so, you see, these are only a tiny, you see that's the plastic flows. Okay, this is the overall supply of the waste, and this is what is separately collected. This is what is commingled, collected, like mixed waste. And the big part of the mixed waste is directly going to waste incineration. And also you see a tiny part is going to the mechanical. We have very few mechanical biological treatment plants. And the plastics which are recovered there, they are finally then sent either to the cement industry or to the waste to energy plant. But at the moment, nothing of those plants is going to the recycling. But this will change in future, yeah, because it is impossible, when we go back here, it's impossible, or maybe a few percentage can be reached of high collection rate, yeah. And for example, for the PET bottles, they try to insert a deposit system. Okay, so this will probably go up, yeah. But for many of the others, people are not willing much more to separately collect. So there are some investigations going on now to recover plastics for recycling out of mixed municipal solid waste. Yeah? So using these mechanical separation processes to advance them, to produce something which is not incinerated, but to produce something which is going to be recycled. Yeah.
Eine Frage bitte.
Yeah.
Films small. Yeah, you're talking about like boxes, small boxes.
I mean, the definition there in Austria for film small is everything which is smaller than this one is film small, and everything which is bigger is film big.
So do you have any answer, any idea why you have a few percent alone? That seems like 18%. 18%, 18% is recycled, but why? It's so
no.
low.
The point is that so much of the material is lost during sorting, and the sorting plants, because we collect the packaging material separately from the waste, from the other waste, and these sorting facilities were mainly trained to focus on other stuff, yeah. And the small films are difficult to be recycled, also, but have no value. You understand? So that's another reason. So there are many issues, and again, if the foil is colored, the value for recycling is going down, because if you have a colored plastic, then you can just go for maybe a very dark plastic product at the end of the day. But if you have, and typically the large films are typically films which are used in industry more, yeah. So they are very often without color, so they have a much higher value. They are much easier to sort it out, and that's basically explained why this works much better than this one.
One very short question.
Yeah.
I was wondering about the waste import that you saw in the first balances. Where does it come from?
Where does it come from?
What is it?
What is it? No, it is basically, I think, on the one hand, I told you that the steel industry is using plastics as a reducing agent. So they get some plastics from Germany and Italy. Okay, that is one part. The other part is, I don't know why, but Austria had from longer time already a rather huge recycling industry, so they get also some plastics from Czech and from Hungary or something like that. Yeah. Other questions? Let's continue. Second one is about steel and steel recycling in the European Union. So a totally different material. But we apply basically the same, because we're just balancing the material, but maybe here was a bit different approach. Situation is like this, and this I need to explain you what was the motivation. Steel, I mean, if you don't know too much about steel, you would say steel is endless recyclable. And this is true also, yeah. But steel is used in different products, you know. I mean, these are very high quality sheets, maybe for the car industry. These are railways, okay, and these are bars used in construction, okay. And the value and also the tolerance of the different steels for impurities is very different. So this has a very high tolerance level, okay, and this one has a very low tolerance level. So basically, when you have this type of steel scrap, you will never be able to make this steel out of it anymore. Yeah. So we have different products and we have different tolerance levels. So that this is one point. The other point is the European Union imports a lot of iron ore. So I think 80% of the iron ore which is needed is imported. Okay, so we import a lot of primary resources. At the same time, the European Union, since maybe 10 or 15 years, is exporting steel scrap, which somehow sounds weird. You know, we import on one hand raw material, which needs to be processed, very energy intensive and very CO2 intensive. And on the other hand, we have already secondary resources, which we don't use, which we export to Turkey. Yeah? And we try to investigate the reason behind that. I mean, the reason was, how to say, more or less, there were some theories behind that, and they are very pronounced, but we try to model that and see if we really can confirm this, okay? So we again had our MFA system with the different processes. I don't want to go into that too much detail, don't want to lose too much time. And we analyzed with this material flow analysis the steel flows in the European Union for the former EU28, so including also UK. And this was not done before. We did that for 1946 to 2017. So we tried to see how it developed over since the Second World War. And we tried to make a projection also into the future, what will happen after 2050. And yeah, as I said, I don't want to explain that in too much detail because it will get much more complicated. You'll see later on. Many of all the blue flows here are taken from statistics. So the steel industry has a very high sophisticated statistics out there. There are European statistical data. There are statistical data from the World Steel Organization. So probably steel is the most, or is the best reported commodity. Probably, yeah. There are a lot of statistics out there. And then a lot of data have been simply calculated because it's very easy. If you know that all these flows are going into the production, okay, you know, all of the blues, you know it from statistics, and there is one missing and it's going outside, you know, you can simply do a small balance and calculate it. Okay. And then we consider altogether 19 different steel products because there are, as I said, how to say, there are rails, there are tubes, there are plates, there are cold rolled coil, and so on. So these very different products which are reported in the statistics, we consider them, and we consider also different sectors which consume these materials. Yeah? Again, as we said before, the packaging sector, construction sector, so quite similar sectors. And the most severe elements for the steel quality, yeah, like unwanted materials in there, which can cause you problems regarding producing certain products, are copper is very important, tin, chromium, nickel, and molybdenum. So we consider these elements in there and make a classification. So we qualified the steel products into 4 quality groups. Those which have a very low content of those elements, which we call it a very high quality or high purity of steel, and a low purity of steel. Yeah? And for example, the reinforcing bars yeah, which are used for the construction of buildings, have a very low purity or low quality. Okay, so these have been assigned based on discussions with guys from the steel metallurgy. And then the next step, that, as I said, it's getting more and more complicated. We have altogether, I don't know, 18 different products of steel. Here we have the rail section, here we have wire rod, which is tubes, coils, and so on. Yeah? And then we have the different sectors where they are used. And again, based on expert interviews, we assigned for different steel products to the different sectors where they use different quality requirements. For example, this one is also a hot rolled narrow strip. It is a kind of sheet. Yeah? And when it's used in the building or infrastructure sector, it's less sensitive to those elements. So it could be also quality tube. But if it's used in other sectors, in the transport sector or in the mechanical engineering, they require high quality standards. And based on all this data, we then calculated this is the quantity of scrap which is generated in the European Union from 1946 or 1945 to 2017 for the different grades. So Q1, Q2, Q3 is the different quality levels. And maybe that's important, I didn't mention, scrap from steel can come from two different points. It can come from the production side. Okay, so when you produce something, you cut something, you get some scrap. This is the fabrication scrap, yeah, or production scrap. And on the other hand, you have the post-consumer scrap. Yeah? And typically, the post-consumer scrap is much higher polluted than the pre-consumer scrap. So all this, which is in the light shaded in the stronger shaded colors, is the new scrap. Quality 1, 2, 3, and 4. And the part here in between is the so-called old scrap or post-consumer scrap. And we see here that this post-consumer scrap increases over time. So more and more scrap is now generated from the usage of products. That has different reasons. On the one hand, we have more and more old stuff which is aged and is thrown away. Okay, so it's post-consumer. On the other hand, the industry became much more efficient over time. You know, like 30 years ago, I don't know, when you make a sheet for a car, you have much higher losses than what you have today because they start to be more efficient. Okay, so here just to compare, in 1950, only 30% of the scrap was coming from post-consumer, okay, and 70% was from production scrap, and in 2017, 60% is coming already from post-consumer, and 40%, which is still a lot, is coming still from the production process. And the main question was now, can we use the scrap what we have for the products we are producing? Okay. So on the one hand, we have a demand on steel qualities based on the products the European Union is producing, and on the other hand, we have the scrap available. Okay. And this we try to display or to compare in this so-called, is it written here, material pinch analysis. Okay. A very complicated word. It simply displays now the different, let's forget about the blue, the red one, the orange one now. Just look on the blue one. This shows you just the crude steel demand of the European Union in the year 1988. And for this year, the quality of Q4 steel was, what is that, 45,000 or almost 50 million tons. And then we had a certain quantity of requirement for Q3. steel, and then a higher amount for Q2, and then finally this is Q1. So this shows you the demand, and the red or the orange line shows you the available scrap. So we have this quantity of scrap of quality Q4, this quality of Q3, and so on. Okay, and as long as the red line is below blue line, everything is fine. So just imagine now, if we would have much more Q4 scrap, we could not use it, you know, because the Q4 scrap cannot be used for products of quality Q3, can be used only for products of quality Q4, yeah. So this is kind of excess scrap, yeah. And this is what we try to simulate and model, and this is now the situation in 2006, okay. And for 2006, we find out that here already, and it was the year before already, this red line or this orange line was overcrossing the blue one, meaning we have this surplus of scrap because we cannot use the scrap, this type of scrap. Yeah? Only if we did dilute it with other sources. Yeah? So we did that for the different years and found out, okay, in the past it was no problem because all the time the red line was more or less below the blue one. And then somehow starting from 2000, the year 2000 or a bit later, we found out that there was starting to be a kind of excess scrap. Here it was 5 million tons, okay? And in 2007, it's already 20 million tons. So forget about all the periods until here because let's put it that way. First start with the just forget about the green line. The orange line here shows you this is the amount of net import or export of scrap from the European Union. It's net export. So until, let's say, until 1990 or something, the European Union all the time imported scrap because the curve is below zero. So there was tiny quantities of scrap imported from other regions, okay, whatever. Then there was, I don't know, 94, about what was it, 1993, there was the first time a huge export of scrap, yeah? And then at a certain time point, okay, it came down again, and then starting from 2000 onwards, the rate of scrap export is really increasing. Which, as I said, is weird. On the one hand, we import a lot of iron ore. On the other hand, we export valuable scrap. And we calculated, as I told you, the surplus of low-quality scrap, okay? And the surplus of low-quality scrap is given by the green line, okay? Of course, at the very beginning, there was no surplus because everything which is negative means there is no surplus, so we could still have more bad scrap used in the European Union. But at a certain time point, that fits very well together, starting from the year 1995, we can show that the surplus of bad quality scrap equals more or less, or shows the same trend than what we are exporting. And this is also what some of the experts in the steel industry says, that they believe it's the bad quality scrap which is exported to Turkey or to other countries. And this was somehow reflected by this model. So we can simulate the past, and then we try to predict it in future. And when we do that, we found out that the surplus of bad scrap will increase until 2050 up to 40 million tons. So we have much more scrap out there. But if we don't change anything, how we manage the scrap or how we separate the scrap, this scrap is lost for the European Union. It needs to be exported. Yeah? And this will increase in future, definitely. And the recommendations, I don't know if it's written here, recommendations was for the steel industry that they need to invest in better sorting technologies, because there are some sorting technologies out there already for the scrap, to better separate the scrap according to some of the, to better separate copper from the iron scrap, because then you have less copper in there, and to invest more in those sorting technologies to avoid that in future more and more scrap is exported and not used. Because that's again something we are talking about circular economy in the European Union. And then we have secondary material today, but we're not using it. We're just, it is recycled there. But I would say if we would like to be, very much independent from primary resources, we should try to use as much of the material we have inside our kitchen. I know that this part was rather difficult to follow. I see those in your eyes. But I would like to show you only what, the program would have needed more time. What can be done with such models also, yeah? Okay. Now I don't know how much time I still have left, because I still have 2 examples. I would like to talk about the CO2 from the waste incineration, if this is still.
So, the people here, so the master students, from Natalia, Rob, and him, they have to go maybe 6:15 or something like that.
Okay.
So
what is the time now?
25 to 6.
Okay. Okay, it's okay.
This one thing, because there was a question in the chat.
Yeah.
So about the plastics.
Yeah.
Someone, Otoniel from Mexico, he asks, what is the thermal treatment method used for domestic plastic waste? In this treatment, so do you take all the plastic that you incinerate to the same thermal treatment?
Basically the plastics which are incinerated, we have 2 different ways of incineration. One is the waste is in the mixed municipal solid waste, and it's just incinerated like what we saw yesterday on a waste incinerator, or the plastics are separated out of the waste and then sent for the cement industry to be incinerated there as a fuel. So these are the 2 ways of thermal utilization of plastics.
Okay, thank you. And one question about the steel.
Yeah.
This question is from me.
Yeah.
So the thing is, well, I do not understand very well this.
Yes.
But so there are systems to separate the scrap to get.
For example, how to say, when we talk about a significant amount of steel scrap is coming from the car shreddering. So you shred the cars here, and a car consists of different qualities of steel also. Basically, you have the sheet, which is another quality than some of the structural parts inside. Okay, so it would be necessary to separate, because if I mix everything together, then I will never get the Q1 quality out of it. Okay, I will just get Q2 or Q3 quality out of it. Okay, so it would be necessary to install something to separate the scrap according from the shredder. So this is one point, and the other point is, which is quite important, also the scrap from the car shredders is usually contaminated with copper. So copper is inside the cars used for cables or whatever, and tiny quantities there rise to the level of copper in the steel, and the copper in steel can never be removed by any processing of the steel. So it's in there, right? It's diluted in there. Okay. Now we come to something totally different. It's about CO2 emissions from waste to energy plants. And this may sound a bit weird, but basically waste incineration plants burn a mixture of waste, a mixture of different materials. And when we burn a mixture of materials, we get CO2, which can be either fossil-based or biogenic-based. And according to the definitions, the biogenic-based CO2 is not accounted for as a greenhouse gas, it's carbon neutral, whereas the CO2 from fossil sources needs to be accounted for. And some European countries have already introduced the waste-to-energy sector into the carbon trading scheme, which is basically the Scandinavian countries. And UK also implemented some kind of national trading scheme for waste-to-energy. And there are today 2 methodologies out there which can be used to do that, to measure that. I mean, you can do it also, how to say, I would say the old-fashioned way. You can go to the incineration plant, take every month a huge amount of sample, sort it with a lot of students. If you have them, if they would like to get a certificate, you can use them. You're doing that here also? We are doing that only one, yeah? No, so you could sort a lot of waste into the different fractions and then do your calculations. But you know, this is so time laborious and so expensive, and you will never get a reliable result because, how to say, you would need to sort so much of the waste because the waste can change also over the seasons. So there are 2 methodologies out there. One is the so-called radiocarbon method. And the radiocarbon method, probably some of you know it, it's applied in dating historical things we find, you know. Because when you find something from a living organism, the carbon-14 decays with a rate of about 7,500 years. Okay, and when we analyze oil or gas or coal, yeah, this material is, how to say, millions of years old, yeah. So the 14C content in plastics is almost 0. It's 0 because it's so old, so it has been totally decayed. And if we look to the 14C content of wood or paper or any biomass, yeah, it is a certain, I don't know the number now, but I just write something down, minus a very tiny quantity, but you can measure this, okay? So in biomass, we have a certain quantity of carbon-14, whereas in fossil materials, we don't have. So the radiocarbon method, they just analyze the off gas, capture the CO2 from the off gas, and then analyze the 14C content in there. And then based on this ratio, they can calculate how much is biogenic and how much is fossil. But you need to take samples and do analysis there. Okay. The other method was developed at our institute. It's called balance method, and it allows also to quantify how much of the CO2 comes from fossil sources and how much comes from biogenic sources. Yeah. And also about the energy. I mean, some of the countries, they focus on energy also because they say if we produce energy from renewable sources, they get a higher feed-in tariff. Okay, but the main question is usually CO2. And this methodology, this balance method, has been implemented in the software, which is called Bioma, and it is also a standardized method. Okay, so I will try now to explain what's the idea behind it and how does it work. Okay. Typically, when we talk about waste or any type of fuel we can combust, we have 3 different materials in there. Okay. Or when we talk about waste, there is water in there basically. Okay. Then there is inert material, like material which is not combustible, so inorganic material, okay? And then we have combustible materials in there. Okay, so this is typically known to divide a food into these three groups. But basically what we did now, we theoretically divided and said the combustibles, in our case, consist of fossil materials, okay, and consist of biogenic materials. Yeah. And the ratios of the different materials, we don't know them. They are unknown, but they are in there, okay? We know there are plastics in there, we know there is some paper in there, bio waste, whatever. We know the water, there must be water in there, and there's some inert material. So there are 4 mass fractions. They are in there, but we don't know the quantity, and we need to calculate it. So this is one point. The second point is when we divide the materials into these biogenic and fossil materials, we know much more about it. We know also almost the elemental composition out of it. Okay? And I will try to explain that now in that way. I have here, okay, that's my ticket. I need that still for tomorrow. If I would analyze, so biogenic material and fossil material consists of carbon, hydrogen, oxygen, nitrogen, sulfur, and to a tiny content, sometimes also chloride, okay? So these are the elements in here, okay? And if I will analyze now any biogenic material in the waste, I will show it to you in the next slide. I will find out that the composition, the elemental composition is almost the same. You know, biogenic material has typically about 50% of carbon, yeah, about, I don't know, 6% of hydrogen, maybe 45 or 44% of oxygen, and then very, very less nitrogen and so on, okay? So by dividing this, we know not only, okay, these are the 4 groups, but we know more, we know some elemental composition about it. And we also know the typical mixture of plastics in our waste, because most of the plastics in our waste is polyethylene and polypropylene, which is very similar. Then we have tiny quantities of PVC, and we have some PET in there. Okay, let's continue, 1 second. So we split up the waste into these 4 groups, but we don't know the mass share. And based on the split up, we can get a good information about the chemical composition. Okay? And we are talking about, this may be important to know, these 2 fractions are water and ash free. Okay? So for example, this paper here would partly be green, partly be gray, because there is also some ash in there, and maybe there is also tiny quantities of water, so also partly be red. But we are just talking about the combustible part which is in there. Okay. So this is the composition, as I told you. For biomass, we have about, as I said, 50% almost of carbon. We have about 6.5% of hydrogen and 44% of oxygen, and then very less nitrogen. For a typical mixture of plastics, it's about 77% of carbon, 11% of hydrogen, and much less oxygen. So we have a very different chemical composition between these 2 materials. This contains a lot of oxygen, yeah, and this contains tiny quantities of oxygen. And what I need to add also, when we do the calculations, we don't take these pie charts as they are here. We consider there is a certain uncertainty in there, you know. We don't know exactly the composition, so we consider an uncertainty range also. So this is, for example, for the different biogenic materials in the waste, yeah, which are in there, and I try to print here the different chemical compositions. And yeah, is not so much different whether we look to wood, paper, garden waste, kitchen waste is a bit different in the elemental composition because there's much more carbon and less oxygen, and textiles look again similar. And this is the average value what we are using, okay? And this is the uncertainty range. Basically. Now, after having this information, we try to set up different balance equations. That's the reason why it's called balance method. And finally, we try to compare this balance equation, this theoretical balance equation, with measured operating data of the plant. Sounds complicated. It is less complicated than it sounds. So altogether, we have 6 balances. Okay. And I will not explain all of them, but just 2 of them, okay? And the most easiest one is the mass balance, okay? So the mass fraction of biogenic plus the mass fraction of fossil matter plus the mass fraction of inert matter plus the mass fraction of water must equal 1, simply by definition, okay? And maybe I'll explain the second one and the third one. The ash balance tells us that the mass fraction of the inert material must equal the ash content of the waste. And do you know how I can easily calculate based on the operating data of the plant? I can easily calculate the ash content of the waste because they know how much slag and how much filter ash is generated. So this quantity divided by the quantity of waste which was inserted is the ash content. So this data, I get it from the operating data of the plant. Okay? And now the third one is the carbon balance. So here it's written the average carbon content of the biogenic material multiplied by the mass fraction of biogenic. So this is about 50%, plus here it was 75% carbon content in the fossil fraction multiplied by the mass fraction of carbon must equal the carbon content of the waste. And the carbon content of the waste can again easily be calculated out of operating data. Many plants, not all the plants, many plants have a CO2 measurement in the off gas, okay? So when I have the CO2 concentration, the off gas multiplied by the off gas volume, I know how much carbon is leaving the system, and all the carbon which is burned is leaving the system, divided by the waste mass, I can get information about the carbon content. Okay? And this applies also for the others. And then we have at the end of the day 6 equations and only 4 unknowns. And out of this we can calculate this. So we have the 4 unknowns, these are the red ones. All the factors which are, simplified, the equations here are simplified, very simplified. Yeah? All the factors which are on the left-hand side are based on the chemical composition, can be derived out of it. And everything which is on the right-hand side can be derived from the operating data. Okay? And very simplified. I mean, we try to show that usually. People who are doing sports, by simply analyzing their breathing, you can calculate whether they do burn carbohydrates or they burn fat. Carbohydrates and fats have a different chemical composition, and this translates also into different composition of the off gas. So if the sum of O2 and CO2 in the off gas is close to 21%, the person is doing carbohydrate burning, whereas when the off gas, the sum of the two gases is getting lower, like 18%, then it's mainly fat burning. Okay, and the same, very simplified, applies. Is also somehow implemented in these equations. When the sum is close to 21%, we are burning mostly biomass or simply biomass, whereas when we go down, it's more and more plastics. one equation in detail might look like this. Okay, yeah.
I have a question.
Yeah.
Can you calculate the various reduction with biounits materials?
What do you mean?
Materials.
Que se puede calcular la profesión igual con el cálculo de material que ejemplo.
Pero ellos no calculan la cantidad de gas. La cantidad de gas la miden y en función de su composición estiman la cantidad que es biogénica y la cantidad que no lo es. O sea, es al revés el cálculo.
Que se usa este cálculo para calcular la producción derivada.
Sí, claro, sería exactamente el mismo cálculo, serían las mismas ecuaciones porque se basa en un balance. Esto genera gas. Si yo quiero saber cuánto gas se generaría de la combustión de esto, lo podría hacer también.
Okay, so no, don't worry. For doing the calculation, these are the operating data the method requires. So it's the quantity of waste, and if there is sewage sludge inside it, also the quantities of ashes is required, the volume of the off gas, the O2 and CO2 content in the off gas, and then some information about the energy production, how much steam is in there, what's the pressure of the steam, and the boiler efficiency. But the most decisive parameters are these two. They are most important for the results. Okay. Before we apply or we insert this data into the equations, we do some plausibility checks to check whether the data are plausible or not. I would like to skip this and come into the results already. So this is like a result out of the methodology. We could calculate it for every month. And we get the average content and the uncertainty. This is our monthly values, and what we analyzed, we can do that also on a daily basis, because the data are just as they are available. We can do that, and we see the fluctuations on a daily basis might be really high, so it might change a lot. The average is here for December, but the data are quite changing over time. So this would be now for one incineration plant, the total quantities of biogenic CO2, which is not accounted for, and these are the emissions they're supposed to pay, and then they have certificates for it. Okay. So 72,000 tons plus minus 3,000 tons. And some operators are also interested to know what is the energy, and how the energy comes from. Because they get higher feed-in tariffs, so in that plant, 46% of the energy which was produced come from biomass. Yeah, we did that, and then we need to validate it to see whether this is reliable or not. We did different things. One very easy validation, or first validation, was we looked to an incineration plant which has two lines. Two combustion lines, but just fed from one waste bunker. Okay, and then we calculate the results and see, okay, they fit very well together. Even if it's changed a lot here suddenly, that's a first validation. Okay, because when they feed from the same place, we expect that the waste is the same. Yeah. So that was a first validation, but of course not the final validation. A next step was we did some trials in Switzerland at 3 incineration plants to compare it with the radiocarbon method. Okay, so they took samples over 3 days, several samples, and we compared it. And yeah, the overlapping or the match was very good, except one sample. Okay, so we have a bigger deviation. So that was a second type of validation. A third type of validation was done in Denmark, where they burned for a certain period just mixed waste, so municipal solid waste and commercial waste, and then for a certain period they changed to wood waste. which was treated. So it was not pure wood, so it was treated with colors or oil or something. And then with the software, we tried to trace what is the biomass content. And it was for the mixed waste about 40%, and then the wood waste was filled in. And then it went up to almost 95% of biomass content, and then dropped again down. And recently we applied that to, in Austria there are 10, 12 incineration plants. We applied that to the different incineration plants in Austria and calculate their fossil CO2 emissions with respect to how much kilograms of CO2 per gigajoule of energy is produced, and find out that the waste looks different in the different region, which can simply be explained by two factors. On the one hand, some of the plants receive commercial waste, and some of the plants don't receive commercial waste at all. And the collection scheme in Austria is different from region to region. So the average value is 42 for all the plants, 42 kilograms CO2 per gigajoule of energy which is produced. And when we compare it to other fuels like oil or hard coal, we see that the waste has a much lower climate impact, of course. Natural gas would have about 55, so we would be also below natural gas. Okay, that was the third part, and I think you're probably tired already. What's the time now?
Not yet.
Not yet, okay. So are there questions for the third part?
So this big difference in the Swedish.
Sorry, what is that?
So this big
Difference,
difference
yeah.
in this
Different plants, yeah.
incinerator
Yeah.
in Sweden. So this big.
So you mean that this one, where we like this one? You mean now?
No.
Switzerland, the previous one is Switzerland.
This one, Switzerland.
Switzerland. I thought it was Sweden.
So it was one sample where we had, when you look, I mean, there was a deviation of about, what is that, 8%? And these are the uncertainty ranges, so there was still some kind of overlap. But so it was not, we were not able to determine what was the reason for this. Other questions? Okay.
Friends, any question from the student?
No, not yet.
Not yet.
So it's the last chance. This one.
Okay. So we're doing still landfill research, which is not so common anymore, I would say, in Europe, because there's not so much funding. But luckily, some years ago, we got funding from the national, fundamental research fund in Austria, which is very rarely. And the idea was to investigate about the carbon and nitrogen metabolism in landfills. Both of them are very important for the emissions of landfill, okay? And I will show you what was the main motivation. Okay, there's still some, okay, forget about this. Landfills, or when we landfill municipal solid waste, it may take very long time to maintain the aftercare, because we have over long period emissions, which are carbon emissions, but also nitrogen emissions. And nitrogen emissions in the form of ammonium, so NH4. Is quite important emission source in the leachate, which requires for a long period of time leachate treatment. These are results from some experiments in Germany, what they did in the laboratory. So they investigated how the leachate emissions. I don't know why this is automatically coming, but it's scaring me. So they investigated on the one hand in a small scale reactor how what I was afraid about. So how the ammonium or the nitrogen emissions develop over time. Yeah. In the laboratory scale, when they have the landfill anaerobic, so without any oxygen in there. And then a second experiment, they did the same, and then they start to aerate, so to inject air. And then what was very obvious, of course, when you start to inject air, you will convert the ammonium into nitrate. Okay, so this one would be definitely converted to nitrate, but they did not observe any nitrate in the leachate. So the overall nitrogen concentration, never mind whether it's ammonium or nitrate, was simply going by almost factor 2 down. Okay? And the only reason for this, or that what they claim at least, was that there was a simultaneous nitrification and denitrification. Because the nitrogen just simply disappeared, okay? And this is somehow difficult to believe that you have these ideal conditions, that you have nitrification and denitrification at the same time. Yeah? So that was the main argument, what we tried to claim, to say we need to investigate what's really going on in the reactors. And we did, I will not show that here now, but we did some isotopic investigation using N15. So we made some tests where we apply this isotope to trace, yeah, but the results are currently under publication, and my PhD student will kill me if I will show you now. That's the reason I will not do that. But I will show you what has been published so far and what we discovered out of it. So the research question was mainly to see where are carbon and nitrogen finally ending up, and also what does it mean. Sorry, I forget to talk about this. What does it mean if we stop aeration? Yeah? Will the level remain here, or will it go back up again? Because that was not investigated or hardly investigated so far. And also, that was what I was talking already. What is the cause of the observed emission reduction? Is it nitrification and denitrification at the same time, or is it incorporation into microbial biomass? Because when you switch from one regime to another, you have different microorganisms active. So probably they just take all the nitrogen for their activities. So yeah. Or another option which we were investigating could be also absorption to a certain extent. So she made some nice experiments. She was most of the time in the laboratory and managing altogether 9 of these reactors. They have a size of, I don't see it here, but the waste volume in there is about 50 liters. Okay. And they are insulated in order to keep the temperature at a certain level. So they are operated at a temperature of 35 degrees. And she was having altogether 9 reactors because she had three different setup of experiments. Okay. So one setup was aerobic, meaning these reactors were most of the time aerated. So at the beginning, every reactor had an initial phase of anaerobic treatment. So it was just put in the waste and then start, let's see how the biogas generation starts. And then after 54 days, these reactors were turned into aerobic, just injecting air. Okay. And then the second group was again anaerobic, then 300 days aerobic, and then switched back to anaerobic operation after 400 days. Another 400 days, and the third group was just all the period anaerobic. Okay? And the overall experiment was about 2 years, so 300, a bit more than 2 years. So some data of the waste, the waste mass in there was about 40 kilograms. Water content was about 26, and we took the material from an old landfill in Vienna, where the waste has been landfilled in the 1970s, so really old waste already. Yeah? the carbon content was still rather high, about 14%. Yeah. Nitrogen content about 5 grams per kilogram trimeter dm. And then RI is the respiration index after 4 days, which was about 6 or 7 to 8. And the gas production potential after 21 days was about 15 liters. So the waste was not so reactive, but still reactive after more than 50 years or 50 years of disposal. And then during the experiments, water was added and also air was added, of course, for some of them, not all of them. And at the end of the experiments, she tried to draw balances for the different elements. And this is now the balance for the carbon, for the anaerobic, anaerobic, and for the anaerobic. Okay. Let's focus on the upper part here. So for the aerobic, we find out that about 20%, 18% is just oxidized of the carbon and leaving as off gas. Very tiny quantities, and this is well known, very tiny quantities of the carbon end up in the leachate. Yeah? The big part remains in the solid, and what we observed also, because he really was very accurate and made balances about the carbon at the beginning and at the end, yeah? She found out that the balance deviation is rather big, which might have several reasons. On the one hand, it might be the case that we lose some of the, because the reactors were opened during the experiments, also to take some samples. So probably will not capture all the off gas. That was one point. The other point is also waste is a very heterogeneous material typically. So when you take samples, solid samples, and do the analysis, you can get different results 2 times. Yeah. But what was weird that the balance deviation was all the time in the same direction. So we all the time are missing some of it. Yeah. So it seems that we lost some of it. Yeah. Of course, when you just compare this one, the aerobic with the anaerobic, we see definitely that during anaerobic degradation, which is not a very big secret, much less of the material is mineralized. Yeah. Here only 7%. Yeah, and much more stays in the solid. Then the same was done for nitrogen. And for nitrogen, she quantified again how much is in the leachate. So leachate is here much more important. How much is in the off gas in the form of N2O. Okay. And the main problem when we talk about nitrification and denitrification, maybe there is some N2 production. We don't know. Yeah. We just call it N2 or balance deviation. Yeah. And this was again. But here we found out the balance deviation was the highest for the aerobic. Could be an indication that there is really simultaneous nitrification and denitrification, because for the anaerobic reactor, where we don't expect this process to happen, the balance deviation is rather small. Yeah? Okay, so that was first a mass balance, and then she was going into some microbial characterization. And one question was whether the nitrogen or the carbon or nitrogen basically is incorporated into biomass, which is generated inside the reactors, okay, during the experiments. So therefore, she used the chloroform fumigation extraction method, okay, which basically applies the following sequence. Here, so you have the sample from the waste, and then part of the sample you just make an extraction with KCl extraction, okay, and then you get all the carbon and the nitrogen, which is just already mineralized in there, but maybe somewhere on the surface or in the water, okay. So this is one part, and the other part she was doing, the other sample, she was using a chloroform atmosphere, meaning by this chloroform atmosphere, she's trying to kill all the microorganisms in there, so they die off. And then she is applying again the extraction. So for the second samples, she not only takes the carbon and the nitrogen which has already been mineralized, but the carbon and nitrogen which is also, how to say, dying off from the microorganisms which are in there. Okay. And when she compares the two samples, then she can calculate how much carbon comes from the nitrogen comes from the biomass, which is generated in there. Okay, this is a common methodology used in soil science. Yeah? And these are the results. I just would like to skip now. So this is the quantities which, when she applied the chloroform fumigation, this is the quantity when you just applied the extraction, and the difference between them is the carbon. That's what you see. That's the carbon in the biomass. Okay. And the experiments show at the beginning we have a certain amount of carbon in microbial biomass, not in the biomass of the waste, but in microorganisms which are degrading the waste, which is about 5. Then it increased because activities inside the reactors increased, so it slightly increased, and at the end of the experiments, the biomass quantity decreased again. And she did that for the different reactors, and we see the same pattern. So for the aerobic, it slightly increased, and at the end of the experiments, because microbial activity slowed down because there was not so much substrate to degrade, so also the microbial biomass went down. For the aerobic, anaerobic reactors, it also went up, then it went down, and when it switched back again to anaerobic, then the biomass concentration, microbial biomass concentration went up again. And for the anaerobic, she didn't take samples because she let them closed all the period. She discovered a strong decline in biomass. Based on these results, she calculated how much of the material in there is, or how much of the carbon is stored in microbial biomass for carbon and nitrogen. And she found out that for carbon, it's about 4 to 12%, which is stored in microorganisms temporarily. And for nitrogen, the share is much higher. So up to 40% of the overall nitrogen present in the waste is incorporated into biomass at certain time points, according to her experience. And then, that's I think one of the last slides. She made also some final leaching tests with KCl. To take samples, leach them, and try to evaluate how much carbon she can leach by applying this extraction. And at the same time, she was doing leaching tests or trying to leach with water only, and see how much is in the water. Mm-hmm. And then there was a quite interesting result which we did not expect. It seems, when we compare, this is like what is totally in there, because when we apply KCl, this is really what, how to say, the total quantity of soluble carbon in there, okay, which can be washed out by applying this. And when we compare these two, we find that the ratio here is very different for the anaerobic than the ratio here, okay? Here, it seems it's much more difficult to leach the material out by water, you know. This is the overall quantity of leachable material, okay? But when we apply just water, we can only hear about, what is that, 20% leach, yeah? And here it's about 50%. And when we look to the material after aeration, just simply by, I don't have a picture now, this material here in there has quite similar, or it has, not similar, but it looks at least a bit like a compost. Having a large surface, having, how to say, some Yeah, probably a large surface where a lot of materials or a lot of nitrogen or carbon can be absorbed. Whereas this material, and we know compost has a high absorption capacity, yeah? Whereas this material is still like waste, as it was, because during anaerobic condition we don't change the shape so much, so we have much lower absorption capacity. So this one I would like to skip it. So we basically find out, or that was published now recently, that a significant reduction of the nitrogen in the leachate when we apply aeration might be explained by the fact that we change the sorption capacity of the waste. So a lot of material is sorbed there, so not really part is maybe really denitrified and denitrified, but a significant part might be also simply just absorbed there, which means if we don't release it, it might claim that the aftercare by aeration is even extended, because if it's there, it's just released over a longer time period. Yeah? Okay, I think that was too much information for you. I'm very happy that you're still awake, or that you claim to be awake. Yeah, I probably have tried too much, but I would like to show only an overview of what we are. And of course, I'm not able to go into that detail to explain. Probably I should bring all my PhD students, and they would be very happy. You know, I could be at the beach, and they have to set me here. Okay, thank you so much. Yeah.
I don't know if there is any question.
I have one question. Yeah. Did you consider the possibility, I guess, of ammonia stripping when you start the aeration?
Of ammonia, yeah.
With the ammonia and ammonia equilibrium, and then stripping with the
stripping,
air with the
that's a good point. The fact is, inside the reactors we have a pH value of about 7.
Yeah, not so high.
Not so high.
Yeah.
So we try to see that, and we have also, how to say, so not that I forget. In the off gas we had a trap, an acid trap. If we have to check, yeah, and there was
a significant amount of ammonia.
Yeah. Thanks for the question. I forget this.
Okay.
Another question.
Just regards and congratulations from Elizabeth from Mexico.
Okay. Nice. Many greetings to her.
Okay. Yes. She's probably. Yes. In Spanish. Right?
Okay.
More questions? Last questions? Yeah, you have to go. Yeah. Okay, so maybe.
Okay.
Master students, you can just.
Yeah.
Y si no, te retiramos para adelante. Como si tú tienes bueno, diferencias, vale, gracias.
Thank you. Thank you. Thank you.
No? No comments. I mean.
What's really interesting,
Okay, thank you.
especially for me, the first part of plastics.
Plastics, okay.
Okay.
So
Tomorrow more, I'm better. I don't think it can be better, but. Okay, thank you. If you don't want to comment anything? Okay. Well,
I'm very
maybe
fine.
Tomorrow, maybe.
if not, on Friday.
Friday, yeah, another check.
¿Te despediste tú y ella?
Sí.
Vale.
He dicho adiós, buenos días.
Vale.
Los correos han sido conmigo,
Tomé varias fotos y vídeos.
Bueno, very good.
Después de